So I wasn't actually sure I was going to do this, but I did a little preparation. And let's get on with it. Rich, of course, has a really powerful history in this community. You know, he was on September 22nd, 1979, when he was in the control room at Arecibo and witnessed the Bayla nuclear blast, along with Lewis Duncan. Wound up going from there to NSF and really started the section that we are now, the upper atmospheric science section, along with Herb Carlson. Rich established the radar chain. He is responsible for CEDAR. CEDAR was originally JBOA, ground-based optical aeronomy, allowed everybody else's nose in the tent, and created a community-wide group called CEDAR. That was followed by Shine and GEM, and is now the community standard, really, for grassroots community development. CubeSats, faculty development, a whole lot of other programs. We're all here today really because of Rich Benke. And of course his diligence for student participation is reflected in many of our careers. So I'll leave it at that and introduce Rich.
No, I was sincere because Aaron Ridley has a theorem that everybody leaves, no matter how long a conference is, everybody leaves at day n-1. And so, you know, for all of you who missed your flights, this is the entertainment for the morning. And I'm really, really appreciating that I got this opportunity, and I'll try to get through it in less than an hour. So yeah, the title is CEDAR, the past, present, some recommendations for the future, but you know, it's not broke, so there's not going to be a lot of recommendations for the future. As Barbara said, we had 349 people, everybody's enthusiastic and happy. Lindsay's doing a great job with the students, and so I'm not going to give you a lot of wise, sage advice at the end, just a few things that I think you might want to keep in mind. And then at the end, I'm going to go into a couple of little reminiscences on some things I worked with besides CEDAR at the and that's going to be it. So what we have? Well, we had CEDAR in the beginning. CEDAR in the beginning sort of started with the original CEDAR plan. I don't know if you've all seen this. This is actually a remarkably good document. I mean, even if I wrote it, and it was done by Tim Colleen and Jerry Romick and many others, and the opening thing here is that's the opening inside cover, and this settles, I think, how old CEDAR is. That's why I brought it up. That's what the date we ought to go with, because I think this is really what started the whole program. It's almost 30 years old. That's kind of a lot. And so you wouldn't expect too many old guys like me still being around talking about it. But, you know, there are, and we'll see that. But I just wanted to point out this, because this is the executive opening summary of the opening CEDAR document, right? And it's remarkably perceptive. I mean, it's actually what we're still doing, and in a good way. Using modern technology would enable important progress to be realized for a broad range of scientific topics which are fundamental and central to understanding our solar terrestrial environment. An essential feature of the recommendations is a coordinated experimental and theoretical approach involving collaborative efforts with other national and international programs. Hey, that is kind of what CEDAR is. And when I said there's still a lot of old guys that were, you know, and women, but you don't get to say that, I don't think. So, I mean, we still see Jeff Forbes is here, for example, in the steering committee, sitting in the front row. David Fritz used to be, he's right back there, okay. And so there's a lot of them, and Rod Heelis, you know, and Tim Colleen isn't here. Ray Roble was here earlier. Bob Schunk was here. So so a lot of people are still here. And you know, CEDAR was broken up into how that was written. That report. There was a steering committee, and we see the people on the steering committee. Jerry Romick was the first chair of the steering committee. Tim Colleen was on it, and Bob Schunk was on it. John Foster, who was here at this meeting, was on it. And then it was broken into subgroups according to instruments. So we had an interferometer, LIDAR, spectroscopy, and imaging subcommittee. And what Bob Curry talked about was I'm going the wrong way. Okay. We also added then to JABOA the radar and the modeling subcommittees. And then that became CEDAR. And so you can see, again, a lot of these folks are still here, and so Vince Wickwar, John Foster, Rod Heelis, and CEDAR has been that way. CEDAR has been a long-standing program of people and then new people coming in and being mentored by old people and gradually turning around. But there's a lot of traditions that go on with CEDAR, and it's a really great place. The first document was the original CEDAR document had 3 phases, and that's how the whole thing was broken up. Phase 1 was the coordination and exploratory phase. And right off the bat, we decided we would have a steering committee and emphasis on instrument clustering, and a few specific campaigns, not many, because we felt we couldn't do much, mean F region winds and temperatures, et cetera. And also then we began to look at new instruments and facility initiatives. And then phase 2 was the science coordination phase. We established the NCAR database. We emphasized getting CEDAR results out in the national meetings, development of modeling capabilities, upgrading instruments, deploying those instruments, and working on what we call Class 1 facilities. And that was supposed to come in a couple of years after phase 1. And then phase 3, 4 or 5, 6 years later, continue working on all of the things above and realize the Class 1 instruments and facilities. And what you can't really read this eye chart, but these were the original science topics that we wanted to work on in phase 1, and then as the instruments and clustering got improved, we would do phase 2, and then once we really knew what we were doing and had all those instruments that we really wanted, we could do phase 3. And the point of all this is, as the instrumentation and the power grew, so did the possibility to do more and more science topics. And so the list is not inclusive, but it illustrates the accelerating rate important coordinated science can be done with the evolving network of CEDAR. So the essential goal, and actually the only thing in this document that is in italics, that I really wanted it to be the only thing in italics, so it was. It is this, in general, the limitations to our understanding will no longer be due to our technical inability to obtain the information required to test current theories, but will be determined rather by, and this is what I wanted, imagination and skill shown in the analysis and interpretation of high-quality data. So that was the idea. The idea is to make sure that the limitations are in the researcher and not in the instrument and the facilities. So that's the goal of CEDAR. And it's interesting, by the way, also this document, the phase 1 the original document, talked about both the facilities program and the aeronomy program helping guide the steering committee. And so I hope NSF gets back to that, and that we both have next year two program directors to help out with and take part in the CEDAR program in this way. And also it's interesting that the construction of instruments belongs to aeronomy, and the facilities are not the instrument place. There's a lot of traditions that we started with CEDAR back in the phase 1 document, and I just wanted to talk about those a little bit. The student introductions, I looked at all the the old literature and tried to find out when was the first time we had the student introductions. Now, I don't guarantee, and Barbara's going to come up and say, I got every one of these wrong, but these are close, all right? These are close. The first authentic that I know of student introduction was in 1991. And it's interesting because not only was the student introduced, but at that meeting, a young postdoc was introduced too. And that young postdoc was named John Saar, and still is actually. And, and so that's great. But this was the original student introduction that I could find. And you can see we were talking about campaigns, and even I gave a little talk, I guess, way back then on budgets and stuff, in which I did a lot of. CEDAR in education. I wrote down the poster winners, and then I gave up after 2007 because the font was getting too small and I was getting too tired of doing this, so we just stopped. But it's amazing, if you're a poster winner, you got a good future. I mean, look at some of the names here. Rich Collins, Susan Nozzle, Denise Thorson. I mean, all of these, John Noto, even this guy, he did okay. The Senator, Farsad, Lars, all of these folks, they're all Mariama, Matsua, Anya Strom, right? I mean, Fabiano, Mike Nichols, Matt Zettergreet. I mean, we pick good poster winners. I mean, this is really good. I mean, that's terrific. Whoops. The tutorial lectures, I didn't go back and, I mean, there's 4 for every CEDAR meter, and the font would really get small. But the tutorials, we were very interested in the students right off the bat, and the tutorials started in 1991, and the first tutorial was given by Dave Fritz, who's at this meeting. And there's been 4 per year ever since then. So we take education really seriously. The CEDAR Prize lectures started in 1989, and the first one I could find was Art Richmond. Amy. Then we had, this is a really great list of who's who in aeronomy, by the way. Mike Mendillo, Craig Heitzel, Colin Hines, Ray John Cho. I'm not going to read it all, but this is really fantastic. And actually all these exist on DVDs. I think every one of these lectures. And if you just wanted to have fun and make sure your library or whatever has these, and watch some of these talks. They're really good. They're really good. Maura Hagen, who's in the front row, she's, Maura, and I'm sure Jeff is in here somewhere. I don't know. If he's not, he should have been. And this is Joe Huba getting the award from John Foster, of course. The CEDAR Postdoc, so you can't read this at all, and neither can I, but the first one was Stan Solomon, and then we go to Julie Moses. There's John Saar was the 4th one there. So we've been at CEDAR Postdocs starting in 1998. And so, and then it kind of merged back. Now NSF has got a postdoc program, and we no longer call it the CEDAR Postdoc. And I don't know if that's a good idea. I think maybe we ought to go back to the CEDAR Postdoc. So see if I still have any friends there and see if we can do that. Here's a tradition that's been broken, and good riddance, right? Finally. Since 1993, I was giving the introduction. I mean, that's like 21 years of saying, welcome to CEDAR. And just when I was getting good at it, right? After 21 years of doing it, now I'm retiring, so I won't be doing it anymore, and somebody who kind of probably is a lot better at it will. But perhaps the biggest success of early CEDAR was, and I think this is the biggest success of CEDAR so far, is building a sense of unified, inclusive community with I mean, we have a tremendously diverse group of young people, young students, older folks, men, women, Hispanics. This is just a great community, and I think CEDAR brings everybody together into that sense of community where people want to help one another, and that's just special. That's just special. Anyway, the next thing was CEDAR, the Phase III document. If you remember, Phase III was when we were going to do all the really great science because we now had the instrumentation and stuff that we really needed. And the editor, that was done in 1996, about 10 years after CEDAR started, and the editor was Jeff Forbes, and the executive summary is pretty nice too. A highly successful research program started in 1986 as a grassroots community initiative. This is another great just definition of CEDAR. For instrumentation that would enable state-of-the-art investigations, broaden to encompass multiple diagnostic techniques. CEDAR is today the dominant national and international research program in terrestrial aeronomy. And it still is today, too, long after this was written. And so, you know, I think you folks should all be proud of yourselves because this is where it's at in aeronomy. Anyway, the Phase III had four major thrusts that they look a lot like the grand challenges in some way. Solar terrestrial interactions, polar aeronomy, coupling with the lower altitudes, long-term variations. And Jeff, for each thrust, he highlighted specific outstanding science issues, which was kind of nice. And one of the things that is included in that book is a list of all the campaigns. And it's kind of interesting to see how many campaigns we did in the beginning. I mean, these were all multi-instrument, multi-investigator campaigns that were targeted after some specific science topic. And they were really all quite successful. And so for the success of CEDAR Phase III science initiative, the continued development of instruments which push the limits of spatial and temporal resolution is a central requirement. That's what Jeff said then. That's still the truth, and we're still working on making that happen. So that led finally to Jeff Thayer, and I'm not going to say too much about this, May 2011, CEDAR New Dimensions. And I think there was even a slight revision to that. This was a really well thought out document. And it brought up a call for proactive development of systems perspective to study the upper atmosphere. The systems perspective is really what this brought to what this document highlighted. This document highlighted emphasis on exchange processes at the boundaries, explore processes related to geospace evolution, developmental, observational, and instrumentation stages, and manage, mine, and manipulate the data. So that was, those were things to keep in mind as you attack your specific problem. You know, emphasize the boundaries. Emphasize the system. And that kind of led, I think, in my mind at least, to the grand challenges that we have today. We have 3 coupling and transport processes from the upper mesosphere through the middle thermosphere, storm and substorms without borders, high latitude geospace systems. All these things are kind of broad. And sometimes you say, well, you know, CEDAR ought to just be more like GEM and focus on something. But you know, that's not our culture. Our culture is be inclusive and allow whatever idea percolates from the community to bubble up and do that. So and so if it fits in one of these categories, that's just great. So now what? What you want to say, this guy is falling asleep. What they're interested in, you got to get in here. This is called the relevance part. You have to talk what people, and so are we still relevant? How's CEDAR doing? Well, I think, whoa, the answer is yes. In fact, more than ever, I think. CEDAR emphasizes exactly the kind of science that will succeed in the future. And to be more specific, I think these are the things that CEDAR really, that we've been talking about so far, that I've been talking about in this talk, and I think these are exactly the kind of things that NSF is looking for. Coordinated collaborative campaigns, instrument clusters, state-of-the-art sensors, complex and fascinating topics that were outlined in Phase 3 in the grand challenges, the strategy of science at interfaces and system science, and be community-driven and inclusive. I think CEDAR is really right on target. And for a while I was wondering that I was afraid we were getting away from some of the really cool campaigns that CEDAR used to do. But you know, I've seen Deep Wave here, and then yesterday Bayla, I even stole the following slide from Bayla. A campaign in South America, this is Marco Mia's, that really epitomizes the kind of science and campaigns that I really like to see. These are, you know, international, multi-instrument, clusters of instruments attacking various equatorial problems. This is just really nice. And so we're not really getting away from our roots, we're staying at our roots, and that's great. But I did want to bring out a couple of things that I think are important, that perhaps we could tweak a little bit and become even more successful. And they have to do with Pasture Quadrant, which, I don't know, probably 90% of the people here, or at least more than half, know what I'm talking about when I talk about the Pasture Quadrant, and bricks versus walls, which is kind of a little bit newer. The Pasture Quadrant, it was a book by Donald Stokes, and in this book, he pointed out that really there's two axes: quest for fundamental understanding and considerations of use. How does it really help anything? How does society benefit? And then he put people in here, or ideas. Pure basic research was in this quadrant, and this is the Pasture Quadrant. Basic research, but it has a real utility. And then pure applied research, he wrote Edison, you know, we know what we want to do, there's no science, we're going to test this wire and see if it explodes inside the bulb or whatever, but you know, sooner or later we'll get it right. But this is discovery and utility. And you know, nobody really wants to take credit for being useless and uninteresting, right? But you know, we've all seen those talks, right? And so what do you do? Well, we have the Mendillo mandate from yesterday. I told Michael that I've now named something after him, which is do discovery science, not confirmation science. I'd say confirmation science is kind of down here. Discovery science is over there. And so what we want to do is make sure you follow the Mendillo mandate, which is try to do something truly cool. Don't just sort of do something incremental. Try to do something beyond incremental, not confirmation. Confirmation and incremental to me are sort of like synonyms here. Do discovery level science. So always push yourself. Always push yourself to the maximum on discovery level science. Then I read this article, and this article kind of hit home too. It's in the Chronicle of Higher Education, and it's bricks versus walls. And let's just look at it for a second. Academic scholarship has become fixated on generating lots of pieces of knowledge, bricks, and is far less concerned with putting them together into a cohesive whole, a wall. And that's sort of Does that strike, that hit home to me. Academic success lies in publishing academic journal articles that make incremental contributions to theory, not in summarizing broader impacts to the community of scholars. We must always try to build the wall from the large and growing body of research in physical scientists on a host of issues. In other words, when you're doing your research, try to fit it into a bigger picture than just, you don't want to just make a better brick, this little thing. That's not going to tell people. But you do want to make a better brick, but you have to put it into perspective, why that's a good thing to do. So there's an example, and I got this example, I stole this example from Bill Latko's tutorial slide. I mean, this really stole it. Look, I mean, you can't steal it more than this, right? But Bill Latko, his first slide in his tutorial, why do or when do we need to worry about the complications of what he was talking about? The MIT coupling stuff. Why? Why do we worry about it? And then he talked about it because it's especially interactive for strong space weather driving. It's especially important for that. Model prediction doesn't do well without coupling. He's putting it in perspective. Utility depends on the fidelity of prediction. Now we're getting really highly into why it's societally relevant. Understanding is demonstrated by prediction. So now he's pretty much maxed out on the relevance scale, and now he goes back to the discovery scale. Coupled the MIT system, the coupled MIT system is exquisitely complex and interesting. So now he's put it totally on the discovery scale, and so we're going to name that the Latko lemma. So along with the Mandela mandate, you have the Latko lemma, and that is when you write your proposal, and you always begin with why it's important, how it fits in. I mean, not what it is. If you write a proposal and say, this is the first measurement of such and such, and we'd like to make it even better next time, right? That's not a good proposal. You have to say why you're doing it, why it's important, why would anybody care? So that's the Latko lemma. So we must continue to strive to pursue, and then I stole this from Dave Heitzel, all these things I guess I take from somebody. But I saw Dave Heitzel give a talk, or he gave me a slide and had these things in it, and I really like them. So we must pursue the most interesting research with real impact, push the envelope experimentally, collaborate outside traditional geospace boundaries, publish in Science and Nature. That sounds a little bit weird, but if you want to actually get people's attention, this community has to publish in journals like Science and Nature, because that's where the visibility lies in our field right now. And put these things together, and we attract the best students. And a lot of the people in this audience, I think, are among the best students. So that's all working, but this is what we must always keep in mind. There's been talk about, how tough times are, but I did pick up this from this meeting and from a workshop we had from Don Farley. So I'm just going to say a few little things about what I think were cool ideas that are still out there, and I hope that get pursued. The idea that Dave Heitzel had at a workshop recently, and I think he might be talking about it even at this one, is a CME radar, a super powerful 50 megahertz radar that can look at the outer ionosphere, the magnetosphere, and even the solar wind. Now, if we can get a radar that can look at the solar wind, then we've combined, you see, we've combined all the geospace science from the mag people to the solar people to the ionosphere people. And so being able to measure a radar measurement of a CME as it approaches the Earth is a really big societally relevant thing. So it would really max out on discovery and utility access, low operation and maintenance, broad support. So I think it would be a good thing, but there's other good ideas out there that we heard Bill Bristow talk about CEDAR Science and HARP. HARP is a big deal. OASIS is the new LIDAR facility. DAISY, you know, the instrument chain of small instruments. And, you know, budgets won't always be bad. It's kind of, right now, this is kind of a downtime, but in some ways, downtime is when you can take advantage of the other guy. Downtime is when they're not actually making any plans. So I think our community ought to take advantage of this time and get ready with some of these ideas so that when the pendulum swings back, which it eventually will, we'll be ready to do some really bold new science. So, so these are some of the ideas that are out there that are really fundamentally important, and I think that we just have to pursue. I mean, you know, just because it's down, you know, don't go for a single all the time. Go for some home runs once in a while too. So I wanted to change now and just talk a little bit about my involvement in a few projects that were kind of fun, really fun, and they worked out pretty well. And so it's the AMISR, you know, the big radar, the space weather, and CubeSats, just some of the stuff. And the AMISR didn't start off as AMISR. I mean, you probably all know that, or maybe you don't know. Or, you know, it had another name, Polar Cap Observatory. And here's the cover of the Polar Cap Observatory, what we thought it would look like. All the contributors, quite a bit of broad community support. This was a really pretty nice booklet put together by Mike Kelly, a well-defined science plan, and it was going to be a phased array on a turret. It looked like the Sonderstrom thing, but instead of a dish, it was going to be a phased array plate. And we wanted to put it the idea was put it in the polar cap near the magnetic pole and do some science that had never been done before. And well, the magnetic pole is there, geographic pole is there. I remember taking a trip with John Kelly, and we flew around to all these little northern islands in the high Arctic, Mold Bay, Isaacson. There's a nice picture that I couldn't find of John Kelly on top of an airplane that was on the runway in Isaacson. I guess you call that a runway. And he was on the wing, sweeping the snow off the wing, doing the de-icing. That was really great. And we flew up to Alert. Alert's about the only place in the world where you can you see a map on the wall that's really pretty big. And on the southern tip of that wall, of that map, is Thule, Greenland. So, I mean, Alert is pretty far north. And so anyway, we ended up at deciding, and it was a pretty easy decision really, that Resolute Bay and Nunavut, that's the name, Resolute Bay was the place to do it because it was the closest settlement to the magnetic pole, and not a huge town, 220 or so. It actually has a jet airport. That's certainly true. It's made out of gravel, so when they put the reverse jets on, it's kind of spectacular, but it does have a jet airport, and it has a regular port, which is pretty important if you're going to, you know, put anything there that's heavy. And it's open usually. It used to be open for only like one ship a year, you know, for a week. But now I suppose it's open more and more. So it goes. It was once described by the people on the HMS Resolute, which is how I guess it got its name. They got stranded there as the most desolate place on the face of the earth. So it's not beautiful, but it's functional. So we put together, I put together a plan based on the science plan, based on our input on the infrastructure, what it would cost, what we could do. And the whole NSF started off at, and this is what I mean, you got to be ready, with the idea of starting up a major research equipment fund. And we were ready with our $30 million or whatever it is request. And we got it in there. We were the first ones to get in there. And I made all these presentations, I can't count them, to the science board, the OMB, to everybody. And so, okay, they approved it. It went to Congress. The House approved it. I mean, and I'm now thinking this, finally did this. This is great. Nothing could go wrong. Well, not quite. This is the austere desk of Senator Stevens in the House Appropriations Committee. You know, all those guys are cutting your budget. This is where they sit. And I ended up actually sitting there talking to a staffer, and the staffer was about maybe the average age of this audience, 30 years old or so, and while I'm talking to him, the secretary comes in and says, "John," his name was John Young, "John, there's three-star generals out there waiting for you." 3-star is pretty high. Three-star generals is a big deal. And he said, "Well, I'm going to talk to this guy for about 20 more minutes. Then I was thinking of having a cup of coffee. Tell him it'll be about 40 minutes. So, okay. That's the way they go. Anyway, Senator Stevens said, "Well, NSF can have the money, the 25 or 30 million in their budget for this, but you got to build it in Alaska." Well, wait, why? Why is that, John? Well, you're just kind of screwed because of salmon fishing. Salmon fishing? I'm trying to build an incoherent scatter radar in Canada, and you're telling me that salmon fishing is messing this up? Yeah, salmon fishing, because Senator Stevens and Alaska are having this war about fishing rights for salmon. And as long as that's not resolved, he has said that no U.S. money will go into anything on Canadian soil. And so you're screwed. So, okay, we're done. We tried it next year, and we could have had the money, but I wanted to put it in the polar cap, so we didn't take the money. We tried next year, the same thing. We tried the year after that. NSF said, "Don't ever ask again. You're embarrassing us with Senator Stevens. He's head of the Appropriations Committee. Don't you get it?" Okay, so we won't do that again. So we had a problem. How do we put the Polar Cap Observatory in Alaska and near the magnetic pole at the same time? Not easy. I mean, it's hard to move the magnetic pole. It's really hard to move Alaska. But it's not so hard to move the radar. And I mean, he was like 80 years old. So we'll make it easy to move, and we'll move it to Alaska. We'll put it in Alaska first, and then we'll move it to Resolute Bay. And that actually magically kind of worked. And in fact, along the way, we'll make 2 of them, and nobody will even notice, right? And so we did. We actually made 2 of them. And the Polar Cap Observatory, we actually made 2.5, like 3 of them, because we partially funded the Canadian one in Resolute Bay as well. So the PCO actually ended up in 2 places, and both in Resolute Bay and in Fairbanks. So that works. The lesson, I guess, is never give up. Because it took a long time. Another reminiscent thing that was fun in the beginning and still is space weather. Space weather started in 1995, really, when George Sisko, Ernie Hildner, Tim Killeen, and Bill Lacko and Lou Lanzarotti came to visit us, us being NSF, myself and Bob Robinson in particular, and with the idea to treat the sun to Earth as a system, and we should be able to make predictions on solar storms and their impacts on the Earth. And they also made a presentation to NASA, but NASA wasn't very interested in it. But we were, and we had a workshop to develop the idea further. And I thought it would be a good idea to call it a national program. I didn't know how to call anything a national program. What do you do? Is there like a official place where you can be blessed and called national? And I found out, well, no, just call it a national program. Put it in the name and see if anybody notices. And if it works, it'll be called a national program. Okay, so we did that. And so we called it a national program. But even before that, we didn't know what to call it. We didn't know what to call this thing of this system of sun, magnetosphere, sun, solar, wind, magnetosphere, ionosphere. So I suggested space weather because, you know, you had solar wind, you had solar storms, you had magnetic storms. It sort of sounded weather-like. And as soon as I said space weather, it sounded good to me. It sounded like I kind of understand it, even though I don't know much about it. It sounds like something people would like. I went down the hall and asked somebody, hey, what do you think of the word space weather? And they said, that's a stupid oxymoron. I mean, space and weather, there can't be any weather in empty space. So, well, okay, I guess that's true, but I didn't believe it, so we used it anyway. And and we came up with this definition in some motel room in Boulder one night at a conference with Bob Robinson and I probably somebody else. And it refers to conditions on the sun and the solar, wind, magnetosphere, ionosphere, and thermosphere that can influence the performance and reliability of space-based, ground-based technological systems and can endanger human health and life and all that stuff. Adverse conditions in the space environment can cause disruptions of satellite operations, communications, navigations, electric power grids, leading to a variety of socioeconomic losses. That sounded pretty good. It's not really a very good definition because I don't think definitions are supposed to say refers to anything. It's supposed to be what it is, but as opposed to what it's kind of like. But it worked, and it was used. It's this sort of pseudo definition was used so many times I can't count it anymore. And we actually started off with a pretty good list of things here, observing what it's about to advance observing capabilities, fundamental understanding, et cetera, forecasting accuracy, education on space weather, in order to prevent or mitigate all of these societally important things. One of the really great things that I really liked, and a lot of people opposed me putting this into the original space weather strategic plan, this statement, but I liked it a lot, so I managed to get it in there. It was from Lou Lanzarote, which is, while it's true that important applications will result from the National Space Weather Program, the science that will be accomplished will be first rate. Indeed, the initiative provides a context in which much of solar terrestrial physics can and should be done. So you see, he's talking about discovery and first-rate science, and also important applications. So here's the important applications, here's the first-rate science. So the reason space weather, in my view, has been so successful is simply this. It's a perfect example of science in the Pasture Quadrant. So I really like it. So as far as how successful, well, in 1994, not a single NSF abstract or for that matter project description contained the term space weather in 1994 or before that. The space weather term didn't exist before 1994 at NSF. I mean, I think maybe if you Googled it, you would find some place where somebody used it, but we had 0.0. In 2014, over 60% of all of the Geospace awards, this is the ones in solar, mag, aeronomy, the abstracts or project descriptions contain the word space weather. So, you know, it really worked. It was pretty successful. And now it's just everywhere. I mean, it's on TV. CubeSats. CubeSats are a great story. I kind of love CubeSats, even though they're, and right now, by the way, there was a hearing that the National Academy is trying to determine how important CubeSats are to science, what science you can really do with CubeSats. And I think they're going to find out you can do a lot of science with CubeSats. So in 27, I kind of heard about CubeSats, and Therese Moretto heard about CubeSats. And so I asked Therese to organize a workshop, and we invited Pete Warden, who was kind of well-known, kind of innovator and creative guy, who was the head of NASA Ames at the time, to give the keynote talk. It was attended by, I was really amazed, 100-some people showed up for this talk. And I found out that these big rockets that go up often have excess launch capability. They put lead in them. I mean, they're able to carry more than they're actually carrying, that seemed just incredible to me, to waste all this launch capability, and that there was a protocol already out there called CubeSats that existed, and they were getting a few secondary launches for what was called BeepSats, where the high school kids would put on these little boxes, and then they would try to determine if they could see them, by looking with somebody's antenna. And so the little BeepSats. But they existed, and the protocol was accepted. And so we began to think at NSF, well, wow, you can get free launches, and there's more and more computing and sensor ability being packed into small spaces. I mean, we all have this tremendous, as you know, this tremendous computer that, imagine putting like 20 of these together, you can fit them in a tiny little box. So the computing and the sensing ability is really, really up there. So what if real engineering and scientific talent tried to see what could be packed into these teeny spaces? I mean, it would be low cost, it would be high risk, but that's okay because it's low cost. Broad student participation, a true change of mindset. I mean, we accept failures. It's not that big a deal if it doesn't work, but we think we can make it work. So, now this looks weird. What the hell am I talking about here? Okay, the problem that I had with CubeSats was when we brought it up, the director of NSF said, we don't do satellite stuff. We do ground-based stuff. And I said, well, but nobody else is doing it. Well, he said, go to NASA and see if it's okay with them that if we do these little satellites. So Therese Moretto and I went to NASA and talked, not to the administrator, that's what they call their top guy, with the deputy administrator at NASA. And he first told us that we were nuts, that it was way too hard, that we couldn't do anything, that we had no idea what we were doing. And then he said, but I said, would you mind though? Would it be okay if we tried it? And his comment was, do you think the makers of Ferraris are worried about the makers of Matchbox Toys? Well, okay. I guess that's a yes, you don't care, right? Okay. So we went back and said, they're okay with us making little CubeSat Matchbox Toys. And our deputy administrator, our deputy director of NSF, Kathy Olson, said, I like it. I'll give you an extra $500,000 to continue making Matchbox Toys. So we started up CubeSats. And right now, they're advancing research in all sorts of areas. I think, by the way, it's nowhere near over. I think far more than just space science is going to get involved in CubeSats. Spurring innovation, creativity, and technology, allowing space missions, enhancing university participation, doing all those things, inspiring and training the next generation of scientists and engineers, and creating new excitement for science and engineering. There's not a lot of things much cooler than launching a rocket into space, a satellite into space. And to be able to do that within a graduate student's lifetime is really special. I went to a launch that a year and a half ago that Doug Rowlands allowed me to go to, and it was a Minotaur rocket, and it's really exciting. It's truly exciting. So the CubeSats, I mean, did it work? Well, our first competition was in 2008. We made 2 awards. There were 27 proposals. Right now we have 7 in orbit, and I think we've funded maybe 8 or 9. But nationally, there are 250 US CubeSats in orbit right now, I found out. That's an amazing number. And it's predicted by 2025, more than 2,000 CubeSats will be in orbit. So CubeSats are what's called a disruptive technology. And they're going to change the way a lot of people think, and in the way that you get a lot of data on the Earth, and so they've been really, really successful and terrific. Since I've been a manager for so long, people wanted me to say something about management and my philosophy on management. Well, that's pretty simple, really. We'll keep it really simple. It's all about trust. Every member of the team must trust every other. And then this is important too, the second bullet. Keep in mind, just because you're the leader doesn't mean you're the smartest person in the room. I mean, you got to really keep that in mind. You're just lucky that you're the leader. And that was certainly true. That's certainly true in my case. And then a word about passion. Hard work and long hours doing something you love is called passion. Hard work, long hours doing something you don't really care about is called stress. Choose A. Okay, I think that's important. And then I'm going to end it with this, because my time's, I see, just exactly up. Remember to have fun along the way. Now, the NSF, when I was there, we had a tradition of Christmas parties. And Bob Robinson, who has written a lot of great scripts and some books, and please buy Bob's book. Bob, I made the plug. Please buy Bob's book on science fiction. But he would write the scripts for the Christmas party. And I remember this particular one where it was a Star Wars kind of thing. And we were aboard the USS Intercourse, and we were being attacked by a spaceship that was in the shape of a large screw, and it had the initials NCAR on the side. I don't know what that stands for, but anyway, we were trying to survive, and then here are the characters in this thing. That's Dr. Spock, who you maybe recognize as Farsad. By the way, Farsad is truly Dr. Spock. We didn't even. That's Anne Marie, who was the nurse, and myself, and that's Laura Waldrop. That's actually Bob Robinson, the author, and our assistant Larissa Patella and Paul Belair, and a fellow in atmospheric chemistry. So. Remember to have fun along the way. That was from our Christmas party in 2012. So I wanted to end by just saying thanks. I want to say thanks to all the CEDAR leaders, and especially everybody who served on the steering committee for all these years, and here's a list of the chairs: Jerry Romick, Tim Colleen, Chet Gardner, Mike Kelly, Jeff Forbes, Michael Mandillo, Joe Salah, Cassandra, who's here. A lot of these people are here. Roger Smith, Sixto Gonzalez, John Soika, who's here too. Jeff Thayer, who's here. John Foster is here. Dave Heitzel and Jeff Semeter, they're all here. And of course, I want to say thanks to Mother CEDAR, who is Barbara Emery. I want to say thanks to NSF for giving me an opportunity to do some really cool things along the way. And I wanted to say thanks really to all the really brilliant people that I had the honor to learn from and lead. And that's Shananda and Cassandra, John Merriweather, excuse me, Bob Kerr, Farsad, Anya, and Anne Marie. By the way, Anne Marie is now going to chemistry, and I think you all ought to give her an applause. And also, Bob Robinson is now retired as well. I think the applause that you give me at the end, if you give me any, should be shared with all of these folks. Therese Moretto, they've all done just a terrific job, and it's been an honor to work with them. And then, of course, most of all, the community for being so diverse, vibrant, engaged, and forward-looking. So I really thank everybody. You've been great. That's right.
Okay, so I can't tell you the sort of number of emails and comments that came into me as in the position as chair about your retirement, and we're delighted that you decided to come to the meeting. We hope that this is just one of many going into the future. Hope you still remain active, but there's no way to sort of encapsulate the gratitude we probably all feel for the work you've done. And so we decided not to worry about that and get you a token instead. And so on behalf of the entire CEDAR community, we have a little gift for you here.
Well,
thank you very much for all your work.
Thanks, John. It's a beautiful. I'll probably drop it. It's a beautiful glass monument or ornament. It's really nice. Thank you so much for the CEDAR community. And again, I do hope I'll stay active, and you are the best. So thanks. Bye.